Hello all, and welcome to this next session of the course Pre-MBA Statistics. So again, like I said in the last session, this is the last week in this short course, and the entire idea we are spending time on this week is on regression modeling. And again, like I said in the last session, we covered a few basics about regression modeling. We talked about the actual population regression model that you see in the slide in front of you. Then we sort of curated a line of best fit idea and so on and so forth. And of course, we talked about several notations such as what do you mean by xi, what do you mean by yi, and for example, let's say what do you mean by yi hat. Okay. So just to briefly understand what do you mean by xi and yi before we begin with any of the intricacies of the model itself. So xi and yi are nothing but the two observed vectors that you're kind of analyzing before you set up a regression model. Now on one hand, xi's are called as either predictors or independent variables, while on the other hand yi's are called as either response variables or the dependent variables. And often in regression analysis, the core idea is to sort of formulate this direction from xi to yi. So obtaining information from xi, and how do you use that information to sort of answer a few questions about the response yi. Alright, now this is exactly where we stopped in the last session. We will sort of elaborate from this point onwards. So again, you see in front of you two equations. So on one hand you have the population regression equation, on the other hand you have the sample regression equation. Now how do you arrive at the sample regression equation is the more important point we will discuss in this session. So again, if you quickly look at the population regression model, which is the first equation here, you see that there are two unknown parameters, namely beta naught and beta 1, and since these are unknown, you are kind of delving deeper into a statistical sort of a relationship, and hence we have to sort of add a random error towards the end. Now at the same time, when you try to estimate the parameters, let's say using the observed xi and yi vectors, then you arrive at what's called as the sample regression line, which is the second equation you see, and the moment you estimate the unknown parameters, we get hold of the predicted yi or the predicted response denoted as yi hat. Okay. Now again, this sample regression line is better called as a line of best fit, and then we saw several examples in the last session where we sort of drew a straight line on the scatter plot, and then that straight line or the red line, which you might have seen in some examples we discussed in the last session, is nothing but the line of best fit. Okay. Now moving on, we will discuss exactly this point as to how do you obtain the line of best fit or how do you obtain the sample regression line per se. Alright, now again I think we sort of talked about the same important point in the last session, that on one hand you have the observed yi, on the other hand you have the predicted response, which is yi hat. So we have to somehow quantify the error that you are making through the regression model. And how do you sort of capture the error? So a very simple idea is to simply take the difference. So yi minus yi hat. Okay, and this is exactly a very important terminology in the regression literature called as residuals and denoted as small ei. Okay, so nothing but the difference between the actual response yi and the one which is given by the line of best fit, you simply subtract them and then you get hold of residuals. And again, residuals, as you may see, are nothing but some sort of errors or more like prediction errors for the ith observation. So every ei is called as a prediction error for the data point I. Okay. Now we want to sort of quantify the idea of line of best fit. So I'll give you a simple example to start with. So imagine that you have a simple scatter plot, and then let me just hypothetically draw some dots here. Now can you think in your minds that there could be infinite number of straight lines, isn't it? So these are just two examples. Another third straight line could be something like this, or there could be something like that, and so on. So there could be infinite number of straight lines plotted on any given scatter plot between xi and yi. Now out of all those infinite lines, how do you sort of find out the line of best fit, or which is also called as a regression line or the least squares line? Okay. So there has to be some criteria which we will put on the prediction errors, or rather ei quantities, because again, like I said, ei's are errors. So one very intuitive sort of a notion is to somewhat minimize those errors or somewhat minimize a function of ei. Okay. Now I'll give you two questions, or rather 2 points, and then you have to tell me that which one should we aim to minimize. So on one hand we have summation ei, on the other hand we have summation ei square, just a function of ei's. Okay. So which one is more apt to sort of minimize? Can you pause the video and try to answer this question? Now the correct answer is the second one, summation ei square, and exactly why? Because if you simply take summation ei, they would cancel out. There will be some positive errors, there will be some negative errors. If you sum all those, this would be close to 0. Okay. So of course the minimum value of summation ei doesn't make sense because it has to be always close to 0, and hence on the other hand we sort of take the square of the residuals, take a sum, and then we somehow try to minimize this quantity. Alright. So this is the entire idea about any regression fitting, or to sort of get to the line of best fit. Essentially what we are doing is essentially we are trying to minimize the summation of squared errors, and hence a more apt name to sort of control all this is called as least squares regression. Okay, so now that we've discussed that which quantity you minimize, now the terminology of least squares regression should come to your mind immediately. Okay, so again just to summarize, since we're sort of trying to minimize summation ei square, and where ei is nothing but yi minus yi hat, and then so how do you compare? So which line is sort of the line of best fit out of all these infinite lines? So whichever line which gives you the minimum value for the summation ei square, because again remember each of these lines individually would yield to some summation ei square value, right? And whichever line out of all these infinite possible lines sort of give you the minimum value of summation ei square, that particular line is called as line of best fit. So we have added a small comment here as well, that a line that fits the data best will be the one for which the n prediction errors are as small as possible in some overall sense. And what do you mean by the some overall sense? Is nothing but you are trying to minimize summation ei square. Okay. So if you keep the small thing in mind, then possibly all the other examples down the line would be sort of easy to understand. So again, if you go back to the same example of height versus weight of 10 students, now let's say you have 10 observations. So I can simply write down or sort of quantify each ei value. So ei is nothing but the distance between the actual observation, for example this guy, and the point on the line of best fit, isn't it? So the deviation between yi and yi hat. So this is exactly your yi, and the point on the line is called as yi hat, which is nothing but the predicted y. And if you do this for each and every observation up to the 10th observation, if you draw those vertical lines, then summation ei square should be minimized. Alright. Okay, so this points to the exact terminology we sort of coined just a short while back, called as least squares regression. So we sort of invoke the least squares criteria, which says to minimize the sum of the squared prediction errors. And unknowingly what we are trying to do is we are trying to find the values of b0, b1. If you remember, we had written down the sample regression line. There you had the two constants b0, b1, which sort of estimate beta naught and beta 1 subsequently. But so in the process of minimizing this capital Q, which is nothing but summation ei square, you are trying to find out the values of b0 and b1 specifically, or more mathematically. Now again, you can pause the video and try to give you a small question that how do you minimize or maximize any mathematical function? So what should be the answer to this question? So how do you minimize or maximize any mathematical function? So you take the derivative, you set that equal to 0, and then you solve for the unknown parameters. This is exactly what we will do here itself. So this is the function you want to minimize, which is capital Q. So you differentiate this in terms of b0 and b1 because you want to find out the values of the estimates b0, b1. Then you get hold of two such equations. You set both those equations equal to 0 and then solve for b0 and solve for b1 simultaneously. Okay. Alright, now again if you come back to the height versus weight example, then in the beginning or rather last session we talked about two specific lines, the solid line and the dashed line. Now if sort of mathematically can you prove that which line is better? Of course visually we sort of postulated that probably the solid line might be better because it's sort of covering many more points as compared to the dashed line. But of course mathematically I can sort of find out the values of summation ei square for both the lines. So for the dashed line it comes out to be 766.5, and for the solid line it comes out to be 599.8. So naturally the solid line is giving you a minimum value for the summation ei square quantity, and hence the solid line is better than the dashed line. Now just to summarize, so where we are at this point is that the simple linear regression model hence becomes this, again just to reiterate, that yi equals beta naught plus beta 1 xi plus epsilon I, where epsilon i's are independent random errors with these assumptions. Expectation is 0, variance of epsilon I sigma square, xi and yi are nothing but the observed data vectors, and beta naught, beta 1 and sigma square are nothing but the unknown parameters in the model. Alright, so now we are sort of through with understanding the model structure, defining the estimates, defining the parameters, defining the idea of residuals, and then how do you sort of make use of the residuals to sort of get hold of some minimum quantity in an overall sense. Okay. Alright, now the more important portion is to understand that the underlying regression model also comes with some model assumptions, alright, and which are very important. So, once you fit a regression model, you would go a step ahead and then try to sort of verify that all the model assumptions are making sense or not. So, we will talk very briefly about certain model assumptions and certain properties about the fitted regression model. Now, very nicely, so you have 4 assumptions which I have sort of coined down into one term called as line conditions. So, LINE. So, each word in this line, or rather each letter in the term line, corresponds to some idea. So, we will discuss that very soon. So, what exactly are line conditions? So, again just to summarize, this is nothing but the regression model we are talking about, and we have 4 assumptions on what quantity really. So, we have 4 assumptions on the error component, because again remember the error component is a random component. Okay. So, the only random component in the entire model are the error components, which are epsilon i's, and since epsilon i's are random, my yi's are also random. Okay. So, this is a very important sort of point to keep in mind always, that yi's are random variables while xi's are kind of fixed. So, we do not treat xi's to be random variables, we treat xi's to be fixed observed quantities, and since the random errors are a random variable, which makes the response to be a random variable, because again remember what exactly is the goal. So, goal is to predict yi and not xi, isn't it. So, whichever quantity you want to predict down the line, that has to be assumed to be as a random variable. Alright, now what exactly are the 4 assumptions of the model? So, the first one is that the mean of the response is a linear function of xi, which is pretty evident from the line of the straight equation that you are seeing in the first equation in this slide. Okay. So, there is nothing which is non-linear here. So, you have a linear model in front of you. So, the mean of the response has to be a linear function in terms of xi. Now, the second assumption on the errors is that the errors epsilon I are independent. So, we sort of assume that the epsilon i's are independent random variables. Third point is that the errors epsilon i's are normally distributed. So, the distribution of the errors is normal. Okay. So, we will come to a point as to what are the parameters there, but again the distribution per se is a normal distribution for the random errors. And lastly, the errors epsilon I have equal variance. Okay. So, all the errors are sort of independent, normally distributed, and they should have a constant variance throughout. Okay. So, very interestingly I have summarized these 4 assumptions in terms of LINE conditions or line conditions. Okay. So, again like I said, the whole purpose of sort of putting forward the assumption is that once the moment you sort of fit a regression model, the very next step is to sort of verify that all these 4 assumptions are being met by the fitted line or not. Alright, now the very important thing is if you are focusing on SLR. So, do you remember what do you mean by SLR? So, SLR means simple linear regression, where there is a single x and a single y. Okay. So, in the context of SLR, it is kind of easy to find out mathematical formulas for B0 and B1. So, again remember that these two are important quantities to us. So, B0 and B1. So, finding B0 and B1 for any line of best fit is an important job to any of the regression modelers, and as long as you are sort of dealing with simple linear regression, we can sort of coin some specific fixed kind of easy looking math formulas for both B0 and B1. Okay. So, again just to start with the same example of heights versus weights of 10 students. So, for this example, this red line is nothing but the regression line that you see here, or line of best fit. And so, again what do you mean by the line of best fit? So, it should have an equation, right. So, yi hat should be equal to B0 plus B1 xi, alright, and this is exactly where B0 and B1 come into the picture. So, for this example I have given you the values of B0, B1. So, B0 happens to be minus 266.53 and B1 happens to be 6.14 specifically for the heights versus weights example. Alright, now again a short while back we discussed that how should you minimize that uppercase Q equation, or how should you minimize to get hold of minimum value of summation ei square. So, again you take derivatives, you set them equal to 0, and this is exactly where you will end up getting these two equations. Then you have to solve for B0 and B1 simultaneously, and at the end of the day you will get these two nice little expressions. So my B1 happens to be nothing but Sxy by Sxx. I am introducing some notations now. So what is Sxy? Sxy is nothing but the cross product of the sum of squares. So summation xi minus x bar into yi minus y bar. On the other hand, my Sxx is nothing but summation xi minus x bar whole square. Okay. So it has to be a ratio between Sxy by Sxx. These are just notations, but mathematically this is exactly what B1 is. And on the other hand, my B0 happens to be y bar minus B1 x bar. Okay. And at the end of the day, once you find out B0 and B1 concretely or rather numerically, you can feed them in this equation to get hold of the fitted regression line or the least squares regression line or the line of best fit. Okay. So again, the whole idea to summarize is that from the data you try to sort of minimize summation ei square. Once you minimize summation ei square, it will lead you to finding B0 and B1. Once you find B0, B1, you feed them into this equation which is called as a least squares regression line. Alright, and now nothing is unknown here now. So each and every entity is known because xi is known to you and yi hat would be nothing but the points that fall on that red line or on that least squares regression line. Alright, so again B0 has a formula which is y bar minus B1 x bar, and on the other hand B1 has a formula which is Sxy by Sxx. Okay. Now very interesting point to note here is that again if you go back the last slide, this is exactly the formula for B0, isn't it? So B0 is y bar minus B1 x bar. If you do a slight rearrangement of this equation, what will you end up getting with? So this implies that y bar would be nothing but B0 plus B1 x bar. So if you take this B1 x bar on the LHS, then and then simply add, then y bar would become B0 plus B1 x bar. And doesn't this resemble the equation of a best fitting line? The only difference is of course in place of xi you have x bar, in place of yi hat you have y bar. Okay. But again assume that you have a scatter plot like this and you have all these random points in the scatter plot, and let's say possibly this is my line of best fit. Now this point x bar comma y bar, if you look at this point, it will be a point on this plane here, x bar comma y bar. So let's say, so what do you mean by x bar by the way? X bar is the mean of x. So let's say the average of x falls somewhere here, average of y falls somewhere here, then the point x bar comma y bar would be nothing but the intersection of these two lines which falls here, okay, isn't it? So this point always falls on the regression line. This is a very interesting and very important point to note or keep in mind always, that the point x bar comma y bar always falls on the line of best fit or the least squares regression line there. Alright. Alright, now again there is no point of sort of going deeper into the notations, these are just brief notations to begin with. So Sxx, Syy, Sxy. So again why do you see a capital S here? Because they denote sum of squares. So either in terms of only x or only y or the cross product between xi and yi, and down the line this is nothing but the sample mean of x and the sample mean of y. Alright, now more importantly, how can we interpret the estimates? I mean finding the estimates is one thing which we have done, which is kind of a good thing, but once you find the estimates, how do you interpret those? So what exactly is the meaning of B0, what exactly is the meaning of B1? So we will spend some time on that front. Okay. Now again let me write down the equation so that things would be easy. So yi hat equals B0 plus B1 xi. Okay. Now you can pause the video and try to answer a simple question, that how do you interpret B1? So we will begin with B1. So how do you interpret B1 to begin with? So the interpretation of B1 is given as a second point here by the way. So B1 is nothing but the estimate of the change in yi hat or change in mean response for every additional 1 unit increase in predictor x, isn't it? So if you increase xi by 1 unit, how much change you will see in yi hat is quantified by nothing but B1, because B1 has been multiplied by xi. So if you increase xi by 1 unit or 2 units or 3 units, then if since you are multiplying that quantity by B1, there will be that much change in the predicted y. Now one small point to note here is yi hat is interchangeably could be written down as mean response, and exactly why I will tell you, because on one hand you have this equation as well, right. So yi equals let us say B0 plus B1 xi, okay, and then now if you take the expected value on, or rather let us say I will write down betas. So beta 0 plus beta 1 xi plus epsilon I, isn't it? Okay, so yi equals beta naught plus beta 1 xi plus epsilon I. Now the moment you take expectations on both sides, what happens is that expectation of yi happens to be beta naught plus beta 1 xi and then plus expected value of epsilon I, which is assumed to be 0. So the expectation of epsilon I, as per the assumptions, you can go back to the line conditions and check one more time that this was taken to be 0. Okay. So again, you can sort of write down either yi hat or mean response, expectation of yi. They are kind of used interchangeably. Okay. So hence, if you see mean response, it means similar to yi hat. So again, coming back to the interpretation, so how do you interpret B1 again? Just to summarize that for every unit increase or change in the predictor x, how much change would you see in the predicted y or the mean response, which is expectation of y. Okay. So again, if you go back to the heights versus weight example, if you remember B1 was 6.14, this means that if you increase a weight of a person, or rather if you increase the height of a person by 6.14, then the weight of a person increases by 6.1. Or rather, let me rephrase this. So if you increase the height of a person by 1 unit, okay, if you increase the height of a person by 1 unit, then the weight of the person increases by 6.14 there. So if you remember, the predictor there was height, response was weight. Okay. Alright, now coming back to how do you interpret B0. So what is the interpretation of B0 now? So again, simply again, if you go back to this equation here, then you can simply see that the moment you put, or rather fix the value of xi to be 0, what would happen? So if you fix the value of xi to be 0, the value of my yi hat becomes nothing but B0. Okay. Hence, B0 is nothing but the predicted response when the value of my predictor, which is xi, is exactly 0. So again, in the student's height versus weight example, if you remember, B0 was minus 267. Thus, if a student's height is 0, his weight is minus 267 pounds. Now again, this interpretation doesn't make sense because weight cannot be negative, but why are you seeing a negative weight here? Because of course, a student's height cannot also be 0. Okay. So an important point to note here is that in the interpretation of the intercept, by the way, B0 is called as the intercept and B1 is called as a slope, exactly similar to how you might have studied in the straight line of equation, or equation of a straight line. Okay. So my B1 is a slope, my B0 is the intercept, and of course interpretation of B0 makes sense only if the value of the predictor is making sense. So in this case, since the student's height cannot be 0, there is no point of sort of quantifying or interpreting B0, which is sort of nonsensical here, which is coming out to be minus 267 pounds there. Okay. So hopefully if you are kind of sure about interpretation of B0, B1, you are trying to sort of do a good job here. I mean, once you fit the regression model, once you check for the assumptions, then how do you interpret B0, how do you interpret B1? So all these are important ideas there. Now sign of slope. So of course, very quickly we will see that when would slope B1 be positive? Of course, if the trend is positive. So in the height versus weight example, you will see that there is an upward trend. So my slope is positive. On the other hand, in the skin cancer mortality versus location example, you have a downward sloping line, so trend is negative. So my slope is also negative there. So of course, sign of the slope, which is B1, depends on whether you have a positive trend or a negative trend there. Now the next thing is very important, called as Pearson's correlation coefficient. So very quickly we will discuss what do you mean by Pearson's correlation coefficient R. So when we talk about any correlation coefficient, I am very sure you must have heard about correlation between two variables very often, right. So whenever if somebody coins this terminology and finds out a correlation coefficient between x and y, they are sort of only focusing or only measuring the strength of a linear association between x and y, okay, and not any kind of an association between x and y. So only focusing on linear association between x and y, and then finding the correlation between the two variables. Okay. So I'll tell you the math formula very soon, but in front of you, you see number of illustrations. So if you have an upward trend and if the line of best fit is somewhat close to all the points in the scatter plot, you will have a stronger correlation, as opposed to that if you have a lot of scatter in the scatter plot and then you have a horizontal line something like this, then correlation value would be close to 0. And on the other hand, if you have a downward trend, then for something like this, and then if the points are close to the line, there will be a negative correlation, of course. So for example, R is minus 0.7 here, and again if there is more scatter in the plot, then you will have a less stronger correlation on the negative side, which is minus 0.3, and again R is 0 in the last case. So depending on whether you have a positive trend or a negative trend, my correlation could be either close to 1 on the positive side or close to -1 on the negative side. Okay. So to summarize, correlation measures the strength of a linear association between x and y. Now, a couple of properties of correlation. So firstly, this is the formula. So we've seen the notation just a short while back. So Sxy and then divided by under root of Sxx into Syy. So if you remember, the classic definition of correlation is nothing but covariance between x and y divided by the standard deviations of x multiplied by standard deviation of y, and this is exactly what this formula is talking about. Okay. Now there are several interesting properties of correlation. So correlation is unitless measure. So there is no unit attached to Rxy. My correlation always lies between -1 and 1, an important property. If correlation is exactly equal to 1, there is a perfect positive linear relationship between x and y. If my correlation is -1, there is a perfect negative linear relationship between x and y. And lastly, if correlation is 0, there is no linear relationship between x and y. So the important point to note from this slide is that we are focusing only on linear relationships everywhere. So either a positive one or a negative one, or close to no linear relationship between x and y. Now the last point, which is again important, estimation of sigma square. So again, where do you see sigma square? If you vaguely remember, one of the assumptions in line conditions was expectation of the error is 0 and variance of the error is sigma square. So this is exactly where you see sigma square, a parameter, and hence estimating the response variance is also important. So it so turns out that since variance of epsilon I is sigma square, my variance of yi also becomes sigma square. So estimating the response variance is also important. So here you will see two thermometer brands. On the left hand side you have type A, on the right hand side you have type B, and of course on the left hand side you have more variance or more scatter, on the right hand side you have much closer values to the straight line, and so on and so forth. So of course, which brand is sort of more useful? Of course the one which is having the lesser variance there. Okay. So up till now, if you are not sitting in a regression course, we have been estimating the variance using a sample variance. So 1 by n minus 1 summation yi minus y bar whole square, and of course there are some properties of S square, that S square is unbiased for sigma square and so on and so forth. But in the case of regression, things are slightly different. So rather than y bar here, we can sort of do better. Okay. So now since you are fitting a straight line, we can sort of replace this yi hat quantity by, or rather we can sort of replace y bar quantity by a yi hat quantity. Okay. And the moment you do it, we have an improved estimator of the variance. So again, if you remember, how do you get hold of yi hat? So I am getting hold of yi hat through the line of best fit, and the only thing I am doing here is I am replacing y bar with an improved estimator of y, which is yi hat, or the predicted response. And if you divide by n minus 2, this is exactly what's the definition of MSE, or mean squared error. Okay. So just to summarize, if you are sitting in a regression course, if you already have a fitted regression model with you, then estimating sigma square could not be done using simply S square, it's sort of meaningless. But an improved estimator of sigma square in the context of regression happens to be mean squared error, or MSE. Now of course in the next sessions we will delve slightly deeper into more properties of regression, we will take up some examples, and then eventually we will talk more about, let's say, some diagnostic checking. So how do you check for the assumptions, right? And ultimately we will close the session with some practical examples to begin with. Thank you.